Everybody, my name is David Mihal. I'm a senior architect at Fuel. Thank you guys for coming in for the talk today. I know I'm kind of like a blank spot on the agenda, so if you came in, you might not have any idea what you're coming in to hear about, but I appreciate you coming to learn a bit about state reduction, which is what we'll be talking about. Talk is called Stay Hydrated because we're going to talk about a technique called state rehydration, which is one of the many things that we are exploring in terms of addressing the state growth issue in blockchains at Fuel. I guess I'll say, if anyone doesn't know Fuel is a project building a new stack, a new operating system for rollups with kind of a whole new VM, language, everything, and really trying to take a first principles approach to tackling a lot of the big problems in L2s today. One of those big problems being state growth. So, before I jump into things, I want to kind of define what we mean when we're talking about state. You guys has everybody heard of like what state is and what the issues are with state growth? Anyone that hasn't heard much about it? There's kind of two things we can refer to when we talk about state. Oftentimes when we talk about state, we're talking about chain state. And chain state is the data that every blockchain, every node in a blockchain needs to hold in order to process new blocks, new transactions. And then there's like user state. User state is the stuff you care about in a blockchain. So how many coins you hold is your state, what NFTs you hold is your state, what the reserves are on some AMM, which sets the price that you can buy and sell at, that's state. So when we talk about, reducing state, when we talk about trying to make, blockchains more stateless, what we're trying to do is we're trying to reduce chain state. We want chain state to be as low as possible because chain state is really like overhead to running a node in the network. And the more we can reduce chain state, the more we can increase user state. Increasing user state is great. That just means we can do more things with a blockchain. So we want to reduce chain state, increase user state. There's no perfect technique to do it. Fuel already has a bunch of cool primitives and things that enable it, but this talk's going to talk about kind of something that's more in the research area of how we're hoping to reduce chain state even more. So this is kind of how a blockchain works. This is where state fits in the process of blockchains processing blocks, processing transactions, creating new blocks. Blockchains are state machines. Every time a new block comes in, what your node's going to do is it's going to take the historical state, it's going to take this big chunk of data that it already has stored, and it's going to take all the new transactions, it's going to execute all the state transitions, run your transactions, run the smart contracts, transfer some tokens, and what it's going to spit out is a new state. And so why this is important is the state itself is really the one key thing that a node needs in a blockchain, that it needs to keep stored. It not only needs to keep stored, but it needs to keep stored in a way that it can quickly access all of its state because new transactions can touch any of that state. Aside from state, there's a lot of history. You've got historic state, that's things archive nodes will hold. You've got transactions, like all the historic transactions. You've got receipts is something else that I haven't mentioned here, but these are things that are a component of a blockchain, but they're not as crucial. Oftentimes, that type of data can be discarded. With EIP 4844 on Ethereum is now discarding basically historic transactions after a few weeks. Not basically discarding them from being part of Ethereum consensus. There's a proposal, I think it's 4444, which also will essentially start pruning the Ethereum history after I think a year. So all this stuff in here we can kind of throw away. It's not that big of a constraint, but the state is. And this state just keeps piling up. It keeps growing over time. The node that you have to maintain gets bigger and bigger and bigger. And this is a massive problem for maintaining the properties we like about blockchains. Because remember, this state needs to be stored by every node in the world. Everyone running an Ethereum node needs the Ethereum state. Everyone running a Solana node needs the Solana state. Everybody running an Arbitrum node or an Optimism node. This applies to L2s as well. And what happens if we don't constrain the state? There's a lot of chains where the state's growing really rapidly, and the blockchains, they keep working. The fees often don't really increase. What you end up with is if state grows unconstrained, it just becomes harder to run a full node. You need to run a server, you need a ton of storage, and we really start to lose like what's so valuable about blockchains, which is the ability for anybody to run a node to verify the state, the ability to not need to go ask somebody else for permission or to ask somebody else for your data. And state is also becoming a key component of the cost of transactions. This is a little bit of like data that we've pulled, just kind of looking at what are the components to your transaction fee. We were looking at optimism, like Uniswap trades on optimism, for example. This bottom one here, probably should be on top, but this bottom one here are the components that made up your fee before EIP 4844. It's basically all call data. It's all data availability. Ethereum introduced EIP 4844. They addressed the biggest bottleneck for Ethereum rollups, and now data availability is like tiny little fraction of the cost. The main thing that's making up your transaction fee on a layer 2 is now mostly state. It's this long-term persistent storage. During congestion, which we're seeing layer 2s hit congestion, it becomes an even larger percentage. So if we want to push fees down, then addressing state is a huge component of doing that. Since Ethereum has come out, Ethereum came out back in 2014, 2015, talking about creating the world computer. We're going to make this computer that everyone in the world has access to, and so people started using it like this big shared database. People were making Twitter apps. They were making. I remember I used like a Ethereum-based job board back in the day. People were basically just writing everything to state in the same way you would just store a bunch of stuff in the database. And every time a blockchain gets congested and the fees go up, we get this reminder that blockchains they're not databases. They're trust machines, and what we're paying for is that trust. And whenever we get this constraint, the things that are the use cases that we're not willing to pay for that trust are the things that get pushed out. And so what we're trying to do with this state rehydration technique is to make the blockchain focus on its key job, which is being a trust machine, being a root of trust, and not treating it like a database, not just writing tons of data to it. We just want to write state commitments, essentially. So how would we do that? I want to go through an example of taking Uniswap v2, kind of one of the simplest applications you can build on a blockchain, and building it using this new technique we're talking about called state rehydration. So simply speaking, this is the components of state on a Uniswap, a Uniswap pool. You've got 7 elements. You can kind of compress this down into 5 different storage slots, but let's call them 7 elements. And there are things like reserve 1 and 0. That's how many tokens are in the pool. We've got some price oracle related things. We've got some fee related things. But we've got 7 different pieces of data that we're storing on every node on any blockchain that has Uniswap v2. Now, a simple way that we can reduce the amount of state that we're storing is, instead of actually storing that state, let's just hash it. We take all this data, we run it through SHA-256. We have a nice 32-byte piece of data, and we're just going to store that in state. So we've now gone from 7 state elements to 1 state element. But now, what would it look like actually using Uniswap? So since we don't have all this data like actually in the blockchain state, but Uniswap still needs to know this data when someone's trying to make a trade, when someone's adding liquidity, when someone's trying to use Uniswap. So instead of having the smart contract load this data out of state, the user has to provide that data in their transaction. So the user, if a user's making a trade, they're going to give the usual data. This is how much I want to swap. This is where I want the coins to go. But they also got to provide all the state, what we would call the rehydrated state. And when the swap goes through, we're going to take all this data. The smart contract will hash it. It'll verify that the data the user provided matches the hash data. Then it's going to do the normal logic. It's going to run your swap. But instead of storing all the data back to state, it's going to do the same thing. It's going to hash that data, update the hash that's in state, and it's going to emit a log with all the uncompressed data. So emitting this log is kind of how anybody can see what the full values are. But again, logs don't need to be persisted in this like highly available state on the nodes of the network. So how would an application, work like this? So basically, all those logs need to be picked up by an indexer. If users going to make a trade, they would go and say, hey, they ask the indexer, like, what's the current state of this Uniswap pool? The indexer gives them that state. The users, their wallet, their browser is going to kind of formulate a transaction that has what they want to do, the user op, or intent, as we can call it. And it's also going to have the state. Package that into a transaction, send it to the network. Simple, right? Now, if this was so simple, how come everybody's not doing this, right? Like, at the very least, we're reducing state, we're reducing fees a lot. This seems like an obvious thing for applications to do. There actually are some applications using this technique. The one that I like to talk about is Uniswap v3, this Uniswap staker contract. It's not a super popular contract, but this is basically a farming contract for Uniswap v3, like concentrated liquidity positions. And Uniswap, they've got a bunch of these state elements, like what is the reward, the pool, start end times. Instead of just storing all that data on the blockchain, they hash that data and store just the hashes on chain. And every time you want to interact with a smart contract, you need to provide all this data in your call data. But again, call data is cheap because it's ephemeral. It doesn't need to be kept forever. State is expensive. So the Uniswap devs, they were able to make this contract a lot cheaper by using this technique. The thing about this example is, this is what, man, I keep hitting the wrong button. This is what we call non-contentious state, because all this data here, it's set once and then it never changes again. It's never updated, it's never deleted, it's never written, so it's really easy to just pull this data off an indexer and anyone can provide it. The problem comes if we have, let's say, contentious state that's changing frequently, state that two different users might try to interact with at the same time. Imagine, in the Uniswap example we had, if there's two people trying to trade, the first guy's going to go trade their coin, it's going to go through, the second person's going to send their trade, but by the time their transaction gets processed, the state's already changed. The state is invalid, and their transaction will fail. This actually happened before on a blockchain. When Cardano came out and launched their state-of-the-art, peer-reviewed, incredible smart contracts a few years ago, everyone was really excited about it until they realized you can't build Uniswap on it. So this is why I call this the Cardano problem, which is if you make a very deterministic system, you don't have the idea of concurrency. You can't have multiple users interacting with the same piece of state at the same time. So how can we address this? To restate the problem is, let's say two people are making a trade at the same time. Those trades end up in the same block, but this technique means that users need to know, they need to know the previous state before their transaction goes in. If you have two trades in the same block, the state's going to change like in the middle of the block. There's really no way of knowing what the current state is. The only person who knows what the state's going to be at that point in time is the person who builds the block builder. So in this model, we're assuming that we live in this modern world where there's a system of block builders, these sophisticated actors. This is how things work today on Ethereum. It's becoming more and more the way things work on a lot of blockchains. We can have the user say, hey, I want to make this trade, and I'm not going to get the state myself. I'm going to tell the block builder to get the state, and the block builder is going to ask an indexer to get that state. They can package this all up. The block builder can rehydrate my transaction, include that state alongside my intent in my transaction, and now all the transactions work normally. All the transactions have the most current state, and yeah, now we can run Uniswap v2 with very minimal state there. So I just threw a bunch of buzzwords out. There's intents, there's block builders, there's MEV, or not MEV, PBS, all these crazy things. This is a cool technique. I hope you guys can see how this is advantageous. The problem is, how do you do this in practice? How do you enable developers to actually build applications using these things? Because a dev's going to look at this and they're going to go like, all right, David just threw out a bunch of crazy words and techniques, but like, I know how to write Solidity. I've written a bunch of Solidity apps. I'm going to keep doing that. We also made a big assumption here of just saying like, hey, let's just ask builders to do things. Builders are sophisticated. They'll do anything we will ask them for. In reality, like most builders, they're profit seeking, like profit maxis. We can give builders a little bit of tip, but if builders need to do lots of crazy customization stuff, that's just not going to happen either. What we need is a system where developers can build applications just as easy as they build them today, and where block builders can serve this purpose, they can serve this new role without much overhead, without additional work. So the nice thing about Fuel is we're building kind of a whole new stack, top to bottom, for Ethereum rollups, where Fuel has a new language called Sway. Fuel is kind of doing a lot of indexing work in-house with a number of partners. We are exploring kind of the block building space and the intent space as well. And by working on all these, we can have them tightly integrated together. Whereas if you try to do these similar techniques on Ethereum, you've got a lot of different pieces of the ecosystem that need to be integrated together. We combine all these techniques, we end up with kind of what feels like a progression of the roll-up architecture that we're already familiar with. Roll-ups, they were able to separate, execution and state, and pull them out into these heterogeneous chains, and leave the layer one, leave Ethereum as the layer responsible for data availability. So the layer one is supposed to be very available, very decentralized. The layer two is supposed to have this really, good execution. That's one thing that we've, been working on a lot up until this point, is building a new virtual machine that's really execution optimized. And if we end up in this world where the state, the user state, ends up not really living on the blockchain nodes themselves, but living more on indexers, now we have another layer that's optimized for state. That's probably more storage optimized. That's going to have a lot more hard drives. It's going to be a lot more kind of available endpoints. It doesn't need to be quite as decentralized because it's just providing this kind of commodified service. And so we kind of have three different layers, all optimized for the role that they're trying to do. And this benefits everybody. So obviously, users get cheaper transactions, right? We've gone from needing to update one state element in the chain to, we've gone from 7 state elements down to 1. So we've reduced the biggest component to transaction fees today. And then the flip side of that is developers can now use a lot more state. What we've really done is we've gone down to a constant, like a fixed amount of state. So a developer that might be used to really trying to optimize for like really small amounts of state, they can store a lot more data in their smart contracts and know that that's not going to lead to huge fees. It's not going to lead to a big burden on the network. Block builders, they now have a new revenue stream if we assume that users will provide a small tip asking for block builders to rehydrate their state. So again, today block builders mostly make their money off of MEV. Now they can still make money off MEV, but they also have this consistent revenue stream as well. Indexers have a nice new business model as well. There's a lot of indexing projects out there. Business models for indexing is, I think, still a little bit up in the air, but this is a very nice kind of decentralized business model for indexers. And finally, node operators can keep running their nodes on consumer hardware. I have an Ethereum node running at home. I want to keep running an Ethereum node at home. I want to keep running the nodes for all the blockchains I care about. This lets us maintain that property and not end up in a world where people have like really huge, where they need really huge, massive servers just to run blockchains. So that's the new technique. We're exploring kind of how to bring this into future versions of Fuel. Hope that was interesting to you guys. If you're interested, would love to hear any questions and to have you join the Fuel community to learn a bit more.
I see the first question here.
And questions already, awesome.
There you go.
Thanks. Yeah, I have a question. So this concept of rehydrating like state, is it mutually exclusive to like predicates on Fuel? Could you talk just a little bit about predicates? Like, and I'll give you a little bit of background. So like, I'm working with Spark that is building a order book on Fuel, and I don't really like know much about Fuel, but I know a lot about this concept of state minimization from Polygon Maiden. So like, I'm really curious about predicates, and do predicates, like this concept of state rehydration, is it mutually exclusive to predicates on Fuel?
Great question. So for anyone not familiar, predicates it's one of the most interesting features of the Fuel virtual machine, the Fuel stack, and they're what I'd call these kind of programmable, lightweight, stateless smart accounts. They enable things like stateless account abstraction. They enable interesting applications like Spark, the project you guys are working on. The techniques I described are definitely not exclusive to predicates. As I showed, like Uniswap is already using kind of a more primitive version of this design for their staker smart contract. So any smart contract can use this technique to reduce the amount of state that they're using. Predicates take this to another level where predicates are inherently they are stateless and that they don't have access to smart contract like typical smart contract state. So predicates, if you want to do something like Uniswap built just with a predicate, you actually really need to do a technique like this. That's kind of the only way to build it. So that's kind of part of the inspiration of this is, smart contracts are a very inefficient way of doing state transitions. We'd like to do things more like predicates on Fuel. So we're exploring what are the techniques where we can build all the applications we want to today using predicates, and this is a way to do it. But yeah, if you're building with smart contracts as well, it's still, I think, just as valuable.
We got time for one last quick question before we move on.
Any questions?
We're moving on, but you're going to be around for a bit?
I'll be around.
Come find David in the hallway somewhere with all your follow-up questions. Thank you very much. Give him a round of
Thank you,
applause.
guys.